airflow through wind turbines or sails can produce significant mechanical power. Windmills are used for their mechanical power, wind pumps for water pumping, and sails to propel ships. But the most frequent, current use is to turn a generator for electrical power. Wind power, as an alternative to burning fossil fuels, is plentiful, renewable, widely distributed, clean, produces no greenhouse gas emissions during operation, and uses little land. The net effects on the environment are far less problematic than those of non-renewable power sources. Wind farms consist of many individual wind turbines which are connected to the electric power transmission network. Onshore wind is an inexpensive source of electricity, competitive with or in many places cheaper than coal or gas plants. Offshore wind is steadier and stronger than on land, and offshore farms have less visual impact. But construction and maintenance costs are considerably higher. Small onshore wind farms can feed some energy into the grid or provide electricity to isolated off-grid locations. Wind power is very consistent from year to year but has significant variation over shorter time scales. It is therefore used in conjunction with other electric power sources to give a reliable supply. As the proportion of wind power in a region increases, the need to upgrade the grid, and a lowered ability to supplant conventional production can occur. Power management techniques such as having excess capacity, geographically distributed turbines, dispatchable backing sources, sufficient hydroelectric power, exporting and importing power to neighboring areas, using vehicle-to-grid strategies or reducing demand when wind production is low, can in many cases overcome these problems. In addition, weather forecasting permits the electricity network to be readied for the predictable variations in production that occur. As of 2015, Denmark generates 40% of its electricity from wind, and at least 83 other countries around the world are using wind power to supply their electricity grids. Wind power capacity has expanded to 369,553 megawatts by December 2014, and total wind energy production is growing rapidly and has reached around 4% of worldwide electricity usage. History. Wind power has been used as long as humans have put sails into the wind. For more than 2 millennia, wind-powered machines have ground grain and pumped water. Wind power was widely available and not confined to the banks of fast-flowing streams, or later, requiring sources of fuel. Wind-powered pumps drained the polders of the Netherlands, and in arid regions such as the American Midwest or the Australian outback, wind pumps provided water for livestock and steam engines. The first windmill used for the production of electricity was built in Scotland in July 1887 by Professor James Blythe of Anderson's College, Glasgow. Blythe's 10 meters high, cloth-sailed wind turbine was installed in the garden of his holiday cottage at Mary Kirk in Kincardineshire, and was used to charge accumulators, developed by the Frenchman Camille Alphonse Fauré, to power the lighting in the cottage, thus making it the first house in the world to have its electricity supplied by wind power. Blythe offered the surplus electricity to the people of Mary Kirk for lighting the main street. However, they turned down the offer as they thought electricity was the work of the devil, although he later built a wind turbine to supply emergency power to the local lunatic asylum, infirmary and dispensary of Montrose. The invention never really caught on as the technology was not considered to be economically viable. Brush. This was built by his engineering company at his home and operated from 1886 until 1900. The brush wind turbine had a rotor 17 meters in diameter and was mounted on an 18 meters tower. Although large by today's standards, the machine was only rated at 12 kilowatts. The connected dynamo was used either to charge a bank of batteries or to operate up to 100 incandescent light bulbs, 3 arc lamps, and various motors in Brush's laboratory, With the development of electric power, wind power found new applications in lighting buildings remote from centrally generated power. Throughout the 20th century, parallel paths developed, small wind stations suitable for farms or residences, and larger utility-scale wind generators that could be connected to electricity grids for remote use of power. Today, wind-powered generators operate in every size range between tiny stations for battery charging at isolated residences, up to near gigawatt-sized offshore wind farms that provide electricity to national electrical networks. Wind farms. A wind farm is a group of wind turbines in the same location used for production of electricity. A large wind farm may consist of several hundred individual wind turbines distributed over an extended area, but the land between the turbines may be used for agricultural or other purposes. For example, Gansu Wind Farm, the largest wind farm in the world, has several thousand turbines. A wind farm may also be located offshore. Almost all large wind turbines have the same design, a horizontal axis wind turbine having an upwind rotor with 3 blades, attached to a nacelle on top of a tall tubular tower. In a wind farm, individual turbines are interconnected with a medium-voltage power collection system and communications network. At a substation, this medium-voltage electric current is increased in voltage with a transformer for connection to the high-voltage electric power transmission system. Generator characteristics and stability. Induction generators, which were often used for wind power projects in the 1980s and 1990s, require reactive power for excitation, so substations used in wind power collection systems include substantial capacitor banks for power factor correction. Different types of wind turbine generators behave differently during transmission grid disturbances, so extensive modeling of the dynamic electromechanical characteristics of a new wind farm is required by transmission system operators to ensure predictable, stable behavior during system faults. In particular, induction generators cannot support the system voltage during faults, unlike steam or hydro turbine-driven synchronous generators. Today, these generators aren't used anymore in modern turbines. Instead, today most turbines use variable speed generators combined with partial or full-scale power converter between the turbine generator and the collector system, which generally have more desirable properties for grid interconnection and have low voltage ride-through capabilities. Modern concepts use either doubly fed machines with partial-scale converters or squirrel cage induction generators or synchronous generators with full-scale converters. Transmission systems operators will supply a wind farm developer with a grid code to specify the requirements for interconnection to the transmission grid. This will include power factor, constancy of frequency and dynamic behavior of the wind farm turbines during a system fault. Offshore wind power. Offshore wind power refers to the construction of wind farms in large bodies of water to generate electricity. These installations can utilize the more frequent and powerful winds that are available in these locations and have less aesthetic impact on the landscape than land-based projects. However, the construction and the maintenance costs are considerably higher. Siemens investors are the leading turbine suppliers for offshore wind power. Dong Energy, Vattenfall and E.ON are the leading offshore operators. As of October 2010, 3.16 gigawatts of offshore wind power capacity was operational, mainly in Northern Europe. According to BTM Consult, more than 16 gigawatts of additional capacity will be installed before the end of 2014, and the UK and Germany will become the 2 leading markets. Offshore wind power capacity is expected to reach a total of 75 gigawatts worldwide by 2020, with significant contributions from China and the US. In 2012, 1,662 turbines at 55 offshore wind farms in 10 European countries produce 18 terawatt-hours, enough to power almost 5 million households. As of August 2013, the London Array in the United Kingdom is the largest offshore wind farm in the world at 630 megawatts. This is followed by Gwent y Mor, also in the UK. Collection and transmission network in a wind farm. Individual turbines are interconnected with a medium-voltage power collection system and communications network at a substation. This medium-voltage electric current is increased in voltage with a transformer for connection to the high-voltage electric power transmission system. A transmission line is required to bring the generated power to markets. For an offshore plant, this may require a submarine cable. Construction of a new high-voltage line may be too costly for the wind resource alone, but wind sites may take advantage of lines installed for conventionally fuel generation. One of the biggest current challenges to wind power grid integration in the United States is the necessity of developing new transmission lines to carry power from wind farms, usually in remote, lowly populated states in the middle of the country due to availability of wind, to high-load locations, usually on the coasts where population density is higher. The current transmission lines in remote locations were not designed for the transport of large amounts of energy. As transmission lines become longer, the losses associated with power transmission increase. As modes of losses at lower lengths are exacerbated and new modes of losses are no longer negligible as the length is increased, making it harder to transport large loads over large distances. However, resistance from state and local governments makes it difficult to construct new transmission lines. Multi-state power transmission projects are discouraged by states with cheap electricity rates for fear that exporting their cheap power will lead to increased rates. A 2005 energy law gave the Energy Department authority to approve transmission projects states refused to act on. But after an attempt to use this authority, the Senate declared the department was being overly aggressive in doing so. Another problem is that wind companies find out after the fact that the transmission capacity of a new farm is below the generation capacity, largely because federal utility rules to encourage renewable energy installation allow feeder lines to meet only minimum standards. These are important issues that need to be solved, as when the transmission capacity does not meet the generation capacity, wind farms are forced to produce below their full potential or stop running altogether, in a process known as curtailment. While this leads to potential renewable generation left untapped, it prevents possible grid overload or risk to reliable service.